So this last example we had in the previous video shows a situation where the limit of the function exists, f at the point of interest exists, but they are not equal. Again, it breaks down. So that's that. Now let's consider yet another example. Well, this. We take f at x to be 1 over x squared if x is not 0, and give it 1 anytime x is equal to 0. Again, this is a case where the function has a value at the point of interest. Our point of interest here is 0. Is f continuous at x equal 0? That is the question. We need again to check conditions 1, 2, and 3. Condition 1, we need to find who f at 0 is. F at 0 is 1, so we are home and right. It exists, no troubles. What about the limit of f at x as x tends to 0? Look, as for x not equal to 0, f at x is 1 over x squared. So we need to look at what is happening to 1 over x squared anytime x is not 0. But then x approaches 0. So we have two ways x can tend to 0. Here, of course we know. It is either way, so we consider the limit of 1 over x squared as x tends to 0 from the negative side. We also consider the limit of 1 over x squared as x tends to 0 from the positive side. By negative side, I mean all values of x that are smaller than 0. So we start from there. Maybe we are starting from minus 10 trillion. We are coming till we start approach 0. From that side. Then to consider the right hand limit, maybe we are starting from plus 20 trillion. We are coming down, getting closer and closer to 0. So you see that in each case, as x tends to 0 from the negative, 1 over x squared will tend to positive infinity. The same thing happens here. As x tends to 0 from the positive side, 1 over x squared will also tend to positive infinity. Therefore, this limit, the limit of 1 over x to the 2 as x approaches 0 is actually equal to plus infinity. And that suggests that the limit does not exist because infinity is not a number. It's just an imaginary symbol to denote a very large number. So this limit does not exist. Therefore, this function is not continuous at the point x equal to 0. So this is another way to verify continuity of the function. All right. I have another interesting example here that we are going to consider graphically. So we see how we can use the graph function to see points of discontinuity and points of continuity. All right. Okay. Look, let's see this function. Whose graph is this one? This is 1, this is 2, this is 3, this is 4. Say this is the point 5. Okay. So what this function, the behavior of this function is that it goes this way. So then continues. It has a value here, and then at this point it jumps, remains continuous at 5 jobs. At this point now, so the point 5 it has a value here. Here it has no value. Here it has no value. Okay. So this is the behavior of the function of interest. I hope you're able to see the graph very well. Now the question is, determine the points of continuity and discontinuity of the function whose graph is on figure below. So we want to check the points of continuity and discontinuity of a function whose graph is here in this picture, in this figure. Okay. First, notice here that at the point 1 there is a hole here on the graph of this function, which means this function is not defined at the point x equal to 1. So f of 1 does not exist. Since f of 1 does not exist, then this function is discontinuous at the point 1. But at the point 2, we have this function is defined. In between 1 and 2, the function is defined. In between 0 and 1, apart from 1, the function is defined. So we have that. And then if you take a look very well, for any point you take between 0 and 1, the limit of this function, both the left-hand limit and the right-hand limit, they exist, and they are always equal to the element of the point of interest. So we have continuity between 0 and 1, discontinuity at the point 1, continuity between 1 and 2, continuity between 2 and 3. But at the point 3, there's a problem. F of 3 is not defined, so the point 3 has a problem. It's not defined here. Sorry, at the point 3, sorry, the value is this. Whatever it traces to here is the value. But then, the limit of this function as x approaches 3 from the left-hand side is not the same as the limit of this function as x approaches 3 from the right-hand side. So because of that, this function is not continuous at the point 3. Again, at the point 5, the value of f at the point 5 is this. So f is defined at 5. But then, as you approach 5 from the negative side, whatever you get as limit is not the same as what you get as you approach 5 from this side. So the limit as x tends to 5 from the negative is not the same as the limit as x tends to 5 from the positive side. That is what this graph suggests. Because of that, this function is discontinuous at the point 5, it is discontinuous at the point 3, it is also discontinuous at the point 1. So let me circle them. These are points of discontinuity. Whereas every other element of the domain of this function, you have continuity of the function. So this is how you can read off discontinuous functions just by looking at the graph. And so it suffices to say that the function is continuous if we can draw the graph of that function without removing our pen from the paper. Do you understand? So a function whose graph we can draw without removing our pen from the paper is said to be continuous within the domain of definition of that function. So with this now, I think we have enough knowledge, enough information about continuity of a function just by applying the 3 conditions listed and then using those conditions to check continuity or otherwise. Alright, the next thing to do is in the next video I'm going to define more formally what we mean by continuity of, or not more formally, I'm going to give an equivalent definition of continuity of a function to the ones we already have, and then we'll take it off from there.